Hi, I am Jacob Farley, and this is my review of Lab 1 Constant Velocity. In this review, I will go through an introduction, the two models that we used, the experiment, the coding, the computational versus experimental results, and then my conclusions based off of that. The main purpose of this lab is to analyze an object's movement while there's zero net force acting on it and plug it into a computational model to see if there are actually zero net forces acting on it. The core concept used in this lab were Newton's first and second laws. Newton's first law says an object in motion stays in motion unless acted upon by an outside force, and Newton's second law says acceleration is directly proportional to the net force acting on an object and inversely proportional to its mass. The important formulas we'll be using are velocity update, position update, average velocity, and Newton's second law. These are the experimental results. They were extremely linear, suggesting that there were very few, if any, forces acting on the cart. And the system and surroundings of the experiment were the cart itself, the friction and air resistance, the tracker that we used in order to use all of the data, GlowScript, what we used to create our computational model, and Google Sheets was used to compare. So we recorded the cart moving along the track, we uploaded and edited the video to Tracker, we created a computational model in GlowScript via the starter code provided, and we transferred the results to Google Sheets. These are the initial conditions at 0 seconds. Our x and y coordinates were extremely close to 0. And we also calculated the initial velocity based off of values from the graph. We found it to be 0.691 meters per second in the x direction. These are our GlowScript initial conditions, where the initial position of the cart was at 0, 0, 0, the origin. Its initial velocity was what we calculated to be the initial velocity of the cart, which was 0.691 meters per second in the x direction, at time equals 0, where the change in time was 1 over 30 seconds. We updated the ball's position by multiplying the change in time by the velocity and adding it to the prior position of the cart. And we did not have to change the velocity of the cart because it is assumed that zero net forces will be acting on the object. Again, we got an extremely linear path. And this is a comparison of the slopes and findings of the two models, where we can see that the computational model has a slightly higher slope, suggesting that the initial velocity was greater than the average velocity for the experimental model. Both charts are extremely close to linear, but only the computational model is actually linear. The computational model also has a slightly greater slope than the experimental model on average. The error or differences from this could have come primarily from human error, where we misjudged lengths in the video through the software, or moved the camera around too much while recording. But it could also be accounted due to forces that we did not account for in the computational model, creating a non-zero net force, like air resistance or friction. And if we flipped the axes, the direction of the x-axis, then the distance traveled of the cart would not change, but the position of it would become negative instead of positive, and velocity would have identical magnitudes, but again would be negative in the x direction instead of positive. And finally, we can conclude that the extreme similarity between the computational model with zero net force and the experimental model tells us that there are net forces, or that there are likely net forces, but they are extremely small. But we cannot determine the number of forces acting in the situation on the cart, only that the net force is primarily in the negative x direction.